we know how to solve exponential and logarithmic equations, the whole point of solving those is because they come up a lot in real-world problems. And so today we're going to focus on solving some real-world problems using these exponential logarithms that we've been learning about. So let's talk about a few of the different types of models that we know. Okay, so we have an exponential growth model. Okay, so here it kind of is just a generic formula, y equals ae to the bx. Now, that particular formula is very, very similar to our PERT formula, and so you can kind of look at that and kind of compare the different variables in it. And so if you look at the a that is in our exponential model, that matches up with the p from our PERT model. And if you recall, p was the principal, and that was always your initial amount. So the a value in this exponential growth model is always going to represent your initial amount. Okay, typically y is going to be the ending amount, so that was the amount of money we ended up with, or in this case it could be other things other than money. Okay, remember E is actually just a number, and so it's the same in both of those formulas. It's 2.718. It's just a number. It doesn't represent a variable of any sort. Okay, sometimes, now in PERT we use the E, but sometimes that E value, instead of having an E there, you'll see the quantity 1 plus R, where R is your interest rate, or maybe is your growth rate. Okay, and then the other thing that we can comment on is the X value. The X value in this formula is really the same as the T value in our PERT formula. So the X is kind of, when we use an X and a Y on our calculator, or it really is representing your time, your T. And so B up here, B is the last thing. B can change depending on what you're talking about. So if you're talking about exponential growth, that B might be something to do with money, it might be something to do with the number of bacteria, it might be population. That B value is a constant that has to do with that particular thing that's growing. Okay, so let's try a problem. So let's say you have $10,000 and you've been told that it will take 15 years to double your money. What's your interest rate and how much will you have in 10 years? Okay, this is actually two separate problems. So let's start with the interest rate question, and let's ignore the how much you will have in 10 years. So using just the information that we have, we're going to look for R, the interest rate. So since this has to do with money, I can use my y equals ae to the bx, or I could really just be using my PERT formula, which is PE to the RT. Same thing. Okay, so since it's money, I'll use the PERT formula, and it says you have $10,000. Okay, that's your initial investment. That's the P, or the A. You've been told that it'll take 15 years to double your money, so that's your time. The question is, what is your interest rate? So I don't know R, but I know that my time is 15 years. And then we just have to use our brain a little bit. If we started off with $10,000 and in 15 years we're going to double our money, then this is going to be $20,000. All right, and so now we're just getting ready to solve. I'm sorry, I goofed up here. Let me go back and erase this here. It's not 10,000 to the R times 15. It's 10,000 E to the R times 15. Okay, so now we're going to do some solving, and we try to get that R value isolated. So the first thing we're going to get rid of is this 10,000. Since it's being multiplied, we're going to divide by 10,000. Divide both sides by 10,000. And then what you get is 20,000 divided by 10,000. That's just 2, which, since we're doubling our money, kind of makes sense that we'd have a 2 over there. E to the, and I'm going to switch that around and call it a 15R. All right, once you get to this point, we're kind of stumped. There's nothing else to get away from that unless I get rid of this exponential. So that's what we're going to do. We're going to get rid of the exponential by switching it to a logarithm. So it's a log base E, so we call that natural log, of 2 equals your exponent. And so at this point we can go to our calculator and we're just going to take the natural log of 2 and divide it by the 15 and we'll have our interest rate. So when I do that in my calculator, the natural log of 2 divided by the 15, and so I'm a little bit out of room here, but divide both sides by 15. And so my interest rate is 0.046209. Okay, and it's a long decimal, and I probably will just say R equals 0.046. But you find with these types of exponential problems that every little decimal place actually kind of starts to make a big difference as that grows over time. And so what I'm going to do is I'm going to store that full value in my calculator. I'll only write the 0.046, but if you can use all the decimal places, you're better off. So if you remember how you can store that, you just do store alpha A. And you can use any letter, I just tend to use A. So now I have that stored. Okay, so now we've answered the first question, what is your interest rate? Well, actually, I should really write my interest rate as a percent, and so my interest rate is actually going to be 4.6%. Okay, now that's the first part of the problem. The second part of the problem says how much will you have after 10 years? All right, so you actually start all over. Now that we know what the R is in this problem, or in this, if you look back, you can think of it as the B. Once you know that, you can reuse that formula, that PERT formula, and do something and find something else out. So I'm going to go back to my PERT formula. And I want to know how much money am I going to have in 10 years. Okay, so I'm asking for an ending amount. How much will I have? If I start off still with the $10,000, e to the, now I know what my interest rate is, and it says in 10 years, so I'll take that times 10. Now since I know it takes 15 years to make 20,000, my answer here should be less than 20,000. And let's just type that in. You're going to go 10,000. You're going to raise it to or take it times e, which is second ln, raised to the 0.046 times 10, close your parentheses, or get out of the exponent and press enter. Okay, and it looks like we're going to have $15,840, and I have 74 cents. Okay, now what I did with this one is I went ahead and just used the 0.046, but I wanted to show you, okay, if we had stored that, remember we stored that as alpha A, so if I were to redo that problem and do the 10,000 second ln and raise it to alpha A times 10, let's look at how much money that would be. So that's $15,874.01. That's quite a bit difference. You're talking $34 there of difference on that. And so, like I said, every little decimal place is important. So I really would prefer you keep that full value and go with your 15,874 number. Okay, you can write it as 0.046, but keep the full value as you do your calculations. All right, let's look at another exponential type of model, but this one's exponential decay. And the reason we know that it's decay is because we have a negative exponent. Remember that you can have, well, so why is B negative? B is negative because we have decay going on here. And you remember what another way to show that? How else might you see that it's a decay problem? Well, instead of the negative exponent, you might have a fraction being taken to a power. So it'll be like this, and then your power is up here. So sometimes it was like a half or something like that. And now in this case, our base value is E. And E is 2.718. So that's bigger than 1, so that would imply growth if it didn't have the negative exponent. All right, if that E value is less than 1, then that's going to show decay. So two ways to see decay. All right, so let's look at this example. Usually we'll use it as a negative exponent just to keep the fractions out of the mix. And so on this problem it says the half-life of carbon-14 is 5,730 years. If there are 3 grams initially, how much will be left in 1,000 years? Okay, real quick reminder of a half-life. A half-life, which for carbon-14 is 5,730 years. What that means is that it will take that many years for me to get rid of half of that substance. So if I start with 3 grams, it'll take the 5,730 years to end up with 1.5 of that. But it continues, it'll take another 5,000 and some years for it to get half of that, and it continues to just get half of it. It doesn't always go down by the same amount, but it'll always be half. Okay, so this is going to be very similar to our exponential growth. We're going to look at the first problem. So we're just looking at this much and hold on to the second part of the question, the 1,000 years. We're not going to use that yet. We're going to use the first information to find out the b. Remember that b changes depending on what you're talking about. So we start off with our formula, y equals ae to the negative bx, and we're going to work through this. I know that the half-life is 5,730. The carbon-14, 14 is not part of the problem, that's just the name of it. There are 3 grams initially. Okay, I know where that goes. That's my A, my initial. Okay, if we're working through a half-life, if I start with 3, then I should end up with 1.5 as my ending amount. E to the negative, I don't know what B is for carbon-14, but X, remember, is your time, and so it's going to take me 5,730 years for me to get down to that 1.5. All right, so let's solve. Divide by 3. 1.5 divided by 3 is a 0.5, which should make sense. Last time we were doing a doubling problem, so we got a 2. This time it's a half-life problem, so we're going to end up with a half. E to the negative, I'm going to switch that around and put my coefficient first. All right, and then I'm just ready to switch forms. Since it's a base E, it's going to turn into a natural log of 0.5 equals my exponent. And then, since you've gotten that exponent out of there, you're just going to solve for B. Okay, so then we should get B, and we just go to our calculator, the natural log of 0.5, close that parenthesis, and divide it by your negative 5,730. And what you get is this super small number. It's actually in scientific notation. You know that because of that E -4 down at the end, or somehow your calculator should show you its scientific notation. Maybe your calculator actually shows the decimal places, but if it's times 10 to the -4th, you have to back your decimal up 4 places, which would end up getting you this number. And again, that's what I'm going to write on my paper, and that's going to be an important number to use, but I'm going to want to use the full value when I do it. So I'm going to do store alpha A. All right, so now, just like last time, we work through the problem to find the B value, and then we start over to actually answer the question. So in this, how much is going to be left in 1,000 years? Okay, so I start off with that same formula. And the question is, how much will be left? So that's what I'm looking for, is that ending amount. The initial amount is still 3 times E to the negative B. Oh, I have that number. It's that negative 0.00012. And X is my time, and so in this case it's times 1,000. And then this can be something I just type in my calculator. Now, I like to kind of predict what my answer is going to be, so I have some idea that it makes sense. So in this case, it took me over 5,000 years to get it down to 1.5. So I'm only going 1,000 years, so it's not going to drop off that much. So I should have somewhere between 1.5 and 3 grams. So here we go. In your calculator, you're going to take 3 times E to the, so you do that second ln, to the negative, and then I can type in the 0.00012, or I'm going to do alpha A times 1,000. And I end up with 2.66. And that's how much of the carbon-14 it's measured in grams, which is somewhere between that 1.5 and 3 that I thought it should be. Okay, so many problems will be like this, where you have to work through the problem here just to get that special constant that goes with the formula. And then you use that, what you found for that constant, to actually solve your problem. Now, not every exponential model has that exact formula. There's a lot of different types of formulas that have exponentials or logarithms in them or something. Here's a pretty common one. It's called Newton's law of cooling. And it looks crazy hard, but it's really not too bad. On your test, I usually give you all the formulas you need, but you need to know them well enough you could plug numbers in so that you know what every variable stands for. Okay, so let's look through this formula. You have T of t. Now that's just function notation. That's the temperature at time t. And so that's really just the ending temperature at a particular time. Okay, that's going to be the ending amount. Okay, T sub m, that's the temperature of the surrounding medium, or sometimes we call that room temperature if you're just talking about something sitting out somewhere. So that's room temperature. T sub O we've talked about is always your initial. Anytime it's sub O, it's initial temperature, or temperature in this case. Minus T sub M, same thing, room temperature. E is just a number to the negative KT. K is a constant that has to do with whatever item is cooling. If it's pizza or water, or in our example, it's going to be coffee. And then T is the time that it takes. Okay, I did not give you very much space for this problem at all, and it is going to take a little bit of space, so I'd recommend flipping your notes over and maybe doing it where you have a little bit more space to work. Okay, so I kind of got a new clean sheet here to work with this problem. And again, it's going to be the kind of situation where you have to work through it to find some key information, and then you have to work through it a second time. So let's look at what we've got. So I'm going to look at this whole first part. I've got a cup of coffee that has cooled from 92 degrees to 50 degrees. Okay, so that's my starting and my ending. So I have my ending, I have my starting. Okay, after 12 minutes, okay, that's the T up here. In a room that's 22 degrees Celsius, that's my surrounding medium. And just with that one sentence there, I have everything except for K. And so if I need to find the K, I'm going to use all of that. So I'll work through it, find K, and then we'll come back to this second question. So here we go. Just filling in numbers. This is my ending temperature. It ended at 50 degrees. Equals the surrounding medium was 22, plus the original was 92, minus the surrounding medium, times E to the negative. I don't know what K is for coffee, and then my time is 12 minutes. Okay, then you have to start solving for K. You have to start isolating it, moving stuff to the other side. So I'm going to subtract my 22. So that's going to get me a 28 equals, I'll go ahead and do my 92 minus 22. And when I write this exponent, I usually like to put the coefficient first. Okay, I can undo this multiplication right here. Let's divide by 70. Okay, and then we'll probably go decimal here on this. And so I have 28 divided by 70. Gets me a 0.4. That came out nice. Okay, equals e to the negative 12k. And now you kind of have pulled out as much stuff as you can. You're ready to switch forms. So let's switch it to a logarithm to get that k out of the exponent. So this will be a log base e, so we write natural log of 0.4 equals my exponent. Divide both sides by negative 12, and I've got my k value. All right, so I'm going to write 0.076, but if you look at your calculator, and you can't just have me do all of this, what you've got to do is type it in yourself, because there's a lot more decimal places, and those are important decimal places, so I'm going to go store alpha A on that. So then I have my K value saved, and so anytime I use my K, I'll go back and get that value. All right, so all of that work was so that we were able to find the K value. So now we start over, and we're going to answer the second question, which is this right here. How long will it take to cool to 30 degrees? Okay, so what that means is now my ending temperature is 30 equals the surrounding medium is still 22 plus the original is still 92 minus the surrounding medium, it's still 22, times e to the negative, and my K value is 0.076. And then what I don't know this time is the T. So instead of a K up there, sorry, that's kind of messy, but I'm going to put a little T down there. All right, so let's clean this up. Subtract the 22 to the other side. So we have 8 equals 70 e to the negative 0.076 t. Divide by the 70. The whole solving process is the same thing. You just have a few different numbers in there. Okay, and now you're at the stage where you're ready to switch forms. So it's a log base e, so natural log of, now I have 0.114 is what I'm going to write. But when I type that in my calculator, I'm going to do natural log second answer, and that'll keep all the decimal places in there. So natural log second answer gets me a negative 2.17, and I'll divide by my K value, which I have stored, remember. So I'll take my answer and I'll divide by alpha A. Okay, so my T is negative 28. Oh, I'm sorry, I divided by a negative, which makes that a positive 28.4, and that's the time that it's going to take, and since the time was measured in minutes, then my answer is 28.4 minutes. All right, so a lot of algebra in that one, a lot of processes to solve the equation, but again, you need to know that formula well enough you know what all the variables stand for so you can plug those in. Okay, so we did some exponential models. Let's talk logarithmic models for a second. I've shown you here a couple types of logarithmic models. That's kind of your generic formula for it, but more often than not, they just give us a particular log formula that we have to plug values into. This particular formula is used to find the Richter number. That is what they measure the magnitude of earthquakes with. So when you think of an earthquake of 7.2 on the Richter scale, that's just telling you, this formula is telling you how they find that 7.2. All right, so in this example, okay, a couple things we do need to know. R is that Richter scale number. The intensity of it, how strong of it is an I, and I sub O is always 1. That's the minimum intensity that we use for comparison. Okay, so it says find the magnitude R of an earthquake of intensity 2 million. Okay, so we're looking for R, and it's going to be log. Now they have base 10, but that's common log. I'd prefer you not even write the base 10. The intensity is 2 million. And we put that over I sub O, but remember I sub O is always 1. So really, I don't know how necessary it is to even write that fraction. Basically, all you're doing is typing in your calculator the log of 2 million, which gets you a Richter scale of 6.3 magnitude. Okay, so then my next question is find the intensity of an earthquake of magnitude 7.3. So this time I'm giving you the R, it's 7.3. So the Richter scale has gone up 1 point. Okay, so now it's a 7.3. And what's the magnitude, I'm sorry, what's the intensity going to be? So log of something over, again, the initial or the I sub O is just a 1. I might rearrange this just a little bit to help you. So I'm going to write it as a log I, forget the 1, equals 7.3. See if that helps you see what we need to do next. We should be, since it's a log, we're going to switch forms and it goes like this. So you should have a 10 to the 7.3 equals I. So then that's just something that you can type into your calculator. What is 10 to the 7.3? And I get, I have a 19,952,623, and I'll throw in a 0.2 decimal. So the intensity of that earthquake, by only going up one value of magnitude from a 6.3 went to a 7.3, it used to be 2 million, now it's almost 20 million. All right, it's because of this log base 10 thing, and it's really just a power of 10. So every time I go up 1 unit, it's times an extra 10. So 2 million times 10 gets you 20 million-ish. So if I was at an 8.3, I'd have to take this times 10, so then you'd be at an intensity of 200 million. So it increases rapidly there. Okay, last one. This is a new type of model. We've done exponential models and we've done logarithmic models, and now this is a new type that we have. It doesn't have the correlation to the exponential as much, but it's called a logistic model, and it does have an exponential piece in it. And typically on these, they're kind of wormy equations, and so I will typically give you all the values. It's just a matter of whether you can work through the algebra to solve them. So for a logistic model, your A and your B and your R in the equation are all just positive constants. E is just 2.718. X and Y are your variables. And A, this is the main value that you'd want to know out of that. A is your limit to growth, that numerator. And so if you look at what a graph of a logistic model looks like, it has this look of an exponential. It starts off and it increases very rapidly, so it's exponential. But what it acknowledges is that not everything will increase exponentially forever, and a lot of times it will start to level off. Some kind of classic logistic models might be perhaps the spread of a disease. Okay, the disease starts to spread rapidly and everybody is getting it, everybody's getting it, but at some point maybe it starts to level off because everybody that is susceptible to it has already gotten it, and so then it levels off. The spread of rumors is like that. It uses a logistic model. First of all, somebody finds something out, and then they share that with their friend, and everybody's sharing it, and everybody's sharing it, and they send it out on Twitter and everything else. But then at some point, everybody knows the rumor, and so it doesn't tend to grow anymore. Okay, so let's look at a logistic example. So this one is the population of deer after T years in Cedar State Park, modeled by this function. So I've given you the whole function. The only thing you don't know is the population at a particular time. It's like your ending population. And you don't know T, the time in which it takes to get to that population. I have 3 questions here. I'm not really going to do them in order. I'm going to do them easiest to hardest. And so I'm going to start off actually with part C. It says, what is the maximum number of deer possible in the park? Okay, well, if you think about what this means is the deer population will increase very rapidly, but at some point there will be too many deer and they'll start to starve, and so it'll start to level off a little bit. That leveling off, remember, is your numerator. So when they ask me what's the maximum number or what's the limit, that's always going to be your numerator. So that would be 1001. That's about the only value that you can just look at the equation and tell what it is. All right, the next one I'm going to look at is part A. It says, what was the initial population? Well, initial population always happens at time 0. That's your starting time. How many deer were there when this all began? So what you do is you plug a 0 in for t. Now, I'm going to do some mental math on this, and I'd like you to follow with me, because this can be kind of messy, but it really works out beautifully. If you're going to plug a 0 in for your t, let's think about what would happen here. So that's going to be 0, and 0 times anything is just 0. So what I really have is e to the 0. Well, e to the 0, or anything to the 0, is just 1. So all of this is really just 1 times 90, that's 90, plus 1, that's 91. So really on this, it becomes 1001 divided by 91. So plugging in a 0 actually kind of simplifies things out nicely. So if I type that in my calculator, 1001 divided by 91, I get 11. Okay, so there were 11 deer to start with. Okay, and I'm sorry, I wrote that kind of in the wrong place. That needed to be up higher, up here. So this is 1100, I'm sorry, not 1100, 1001 divided by 91, which ends up getting us 11. Okay, so this next one, part B, this is the one that's kind of messy. In fact, I'm going to need a lot more space to solve that one so it doesn't get too cluttery. So you're probably going to want to find some extra scratch area on your notes to do this one. Okay, I pulled out the key information here. I need my formula, and I want to know when the number of deer will be 600. So there's really only two variables left in here. This is my ending number of deer. This is my time. And so I know that my ending number of deer is supposed to be 600, and I'm trying to solve for the time. So I'll have 600 equals 1001 over 1 plus 90 e to the negative 0.2 t. All right, so to solve this thing, I'm going to have to get rid of this fraction. So this whole denominator, I'm going to multiply both sides by that whole denominator. I'm going to be kind of lazy here. I'm just going to write this in parentheses like this. But if I can multiply by that denominator, then this will cancel out. And over here on the left side, I'm going to have my 600, but it's going to be multiplied by that denominator. And it will equal 1001. So now we're just trying to solve for this t, so let's start isolating stuff. Let's get rid of the 600. That's a 1.66. It's going to be important that we keep those values in our calculator as we go through this. So don't ever clear it. Always keep all the decimal places there. So with that, I'm just going to hit -1 to move the 1 to the other side. So then I'm going to have a 90 e to the negative 0.2 t be equal to 0.668. And then I'm going to divide by 90, so just do divide by 90. And I'm going to have e to the negative 0.2 t equals 0.007. And then I'm ready to switch forms, so since it's a base e, it'll be a natural log of 0.007 equals negative 0.2 t, and just divide by the negative 0.2. Again, a lot of algebra here on getting the variable isolated. So what I'm going to do on my calculator is I'm going to do natural log second answer. That way I don't use the rounded off version. And then I'm going to take that answer and divide it by negative 0.2. And so what I end up with then is 24.5. And that's the time that it takes, so that's measured in years. All right. That's all I have. A lot of different models. Be able to use these formulas that we've been talking about. And just on the basic ones, the exponentials, that you can set one up by yourself. A lot of times I'll just give you the formula and you have to work through the algebra to solve. But hope this helps. Good luck.